Hey there, kids. Welcome to our Lesson 12 e-lecture. We're talking about 3D surface measurements here, and some of you have already done a lot of work on your try-its. I appreciate that. Keep going. Just give you a little bit of stuff that you probably should have picked up already. If not, a little bit of help on what you should have picked up. So we start with a normal field, a three-dimensional field there, and the divergence field formula is pretty much the same in 2D as it is in 3D here. So if you remember, basically we just take full partial derivatives and add them together. So in 3D, we're looking at this. The derivative of m with respect to x. The derivative of n with respect to y. And the derivative of p with respect to z added together. All right, and that brings us to Gauss's formula in 3D, which we did in 2D a few chapters ago. Basically just tells us that the triple integral over the region R of the divergence of the field excuse my bad handwriting, is the same as the double integral of some region C of field dot outer unit normal dA, and they both give us the net flow of the field across that region C. Formula always holds if there's no singularities, but it might and probably will fail in the presence of singularities. Okay, sources and sinks. A point is a source if at that point the divergence is greater than 0, and it's a sink if at that point divergence is less than 0. Area calculations, a couple ways that we can do this. We can do the magnitude of the cross product of two vectors, or we can do magnitude x, magnitude y, sine theta. Both of those will give us the area of a parallelogram defined by two vectors x and y. All right, so the last couple chapters we've been talking a lot about area conversion factors. So now we're going to do a surface area conversion factor here. Essentially just the magnitude of the cross product of the u and v that we are converting to. Okay, so that kind of looks like here. Cross of uv would be dx du, dy du, dz du, cross dx dv, dy dv, dz dv. That cross can also be called normal uv as well. So here we have an example of it. We're trying to calculate the surface area conversion factor using this conversion here. So first we do our partial derivatives with respect to u and with respect to v. Okay, and then we take our cross product. And finally, find the magnitude of that cross product. So our surface area conversion factor would be root 14. All right, interpreting the net flow across a surface rather than a solid here. Just reading along there, if you measure the net flow of a field across a solid, you can interpret whether the net flow is from inside to outside. What about a surface that does not form a closed solid? So basically, what we're thinking of there is we're thinking about like a carpet. You know, is the flow going from over to under, or is it going from under to over? That's all about perspective. Basically, you have to pick a top side when you're talking about surfaces that are not a closed solid. The sign of your calculation basically tells you whether or not your vector field is with or against the normal vectors, whose magnitude, of course, represent our surface area conversion factor. Okay, we use a conversion factor to do substitute curves. So a couple last things here. If the div field happens to be 0, that means all that. Which then, of course, tells us if we're talking about between two fields, if it's 0, then those two have to be 0. Have to be equal to each other. The only way to get 0 is if both these two are equivalent. That's the last thing here. If you do have a singularity, just like when we did back in chapter, I want to say 5, basically just put a small sphere around it instead of a circle this time because we're in 3D. And do the double integral of the sphere of the dot product of the field, the outer and normal, which of course you can use substitute curves for if necessary. All right. If you have any questions about this, please let me know. Otherwise, keep working.